Okay, then we are online. Yes, so welcome to now it's obviously the 9th lecture in Introduction to Multiple, to a Lattice Boltzmann method. So today we talk about the multiple relaxation time method, and I hope that some of you have some time, because I've decided that I will add, because last time it worked actually pretty well with the coding session. I decided that I add a small coding session. I don't know whether it's going to be small or not afterwards. So this is the third hour that I'm always talking about. And also we have to cover a little bit of ground. So if you have to run away after this, yeah, it will be on the recording. And in my opinion, there are some interesting things to discuss also for the more advanced listeners. Okay, multiple relaxation time. Yeah, we start first with some efficiency consideration. Yeah, why we have why we are probably not completely satisfied with what we had last time with our BGK methods. Efficiency considerations. So, number one. Okay, now our general problem that drives our field is that the CFD is in general very expensive. So this is something that we have to live with, and we always try to find ways to minimize our cost. And this can also be regarded in an asymptotic way and be analyzed with so-called performance models. Yeah? So now we start with trying to model our performance, where for this we introduce some variables. So the computational cost, yeah, it's not very well defined. We come to this, and we define a domain size. So how big is our problem? Of course, this, if you ask for more, you have to pay more, obviously. So this here is a volume, typically in 3 dimensions. And then you have a duration of the simulation. This means we are talking about transient simulations in Lattice Boltzmann. D, this is the question for how much time are you simulating. And with this, I mean the time in the simulation, not the time that it takes to simulate. Yeah. And then there is, in order to evaluate this, we need some performance measure. And this performance measure P, which here we use so-called node updates. Node updates per second. So second means this is the time that the simulation actually, that we need to run the simulation. So it's the wall clock time. Yeah? And this is apprehended in the Lattice Boltzmann world as NUBs. Yeah? So some people will ask you, how many NUBs does your code have? Yeah? Usually they ask how many mega NUBs your code has, or nowadays they will usually ask you how many giga NUBs your code has. So if you still have mega NUBs, then you're probably not using a modern computer. Okay, so let's look at our performance then. The performance will be given by the number of lattice nodes times the number of time steps divided by the complete time that the simulation takes. So this is the wall clock time. And this will be given in TUBS. So, what is the number of lattice nodes? We live in a three-dimensional world. This means the number of lattice nodes, we call it n, is equal to the volume divided by delta x. What am I doing? Delta x to the cube, obviously, right? Then, what is the number of time steps? Very simple. Time steps. Let's call it t. This is the duration of our simulation divided by the length of the time steps. So then we can compute the cost of our simulation, or we can define the cost of our simulation as the number of nodes times the number of time steps divided by our performance. And this can then be obviously expressed in what we have above here. So the volume times the duration divided by the performance, delta x to the cube, and delta t, just delta t. So what's immediately we see by looking at this is that delta x has a larger impact than delta t. Okay, let's. I mean, this is absolutely trivial, but it's just so much simpler to increase your times, to try to increase your performance by increasing the time step, because this is a single variable that you have to set in your code. Whereas increasing the crit size has much more implication and you need to remesh and interpolate and things. So yes, it's trivial, but still it's tempting to try to improve your performance by making a longer time step, which is often not very successful. So, and of course, there are some constraints on these things. So you cannot just choose them the way you want. Yeah? You have constraints on these things. Constraints on delta x and delta t. So, first things first, the world would be a much easier place in numerics if we just cared about stability, yeah? And then our life would be much simpler, and sometimes we pretend we only care about stability, but what we are actually caring about is accuracy. So this really is a beast. Because, I mean, in principle, it means delta x, delta t, the smaller the better. It is not easy to really assess the accuracy of what you are doing. Yeah, because it's difficult to know what your accuracy is. It's also difficult to know from, so first of all, you have to decide what accuracy you want to have. Then you would have to assess this, whether you actually get this accuracy, and then you have to decide on this how to set your delta x and delta t. Yeah, so this is pretty difficult to do. What is much easier to do is to talk about just stability, because then you see. Yeah, so you make your crit a little your crit spacing a little larger, so then it crashes. Yeah, so you may be upset that something crashes, but crashing code is your friend. Yeah, because when it crashes, you know accuracy is low. Gone. Yeah, and the bigger problem is that you have a running simulation that gives you some result, and you don't know about its accuracy, and its accuracy may be bad because you use delta x and delta t too large. Okay, so this is very difficult. So we try to do something simpler. Yeah, just work with stability. And stability is in this kind of methods given by the CFL condition. That means there is a maximum speed that we can deal with. And the speed is so this is a pretty simple thing. So the speed, let's call it u here, and we'll take the magnitude of this. This must be smaller than 1 delta x by delta t minus the speed of sound. Yeah? So because this is how information is traveling. So we have to add these two things together. This is okay. It can move one grid spacing in one time step. This is what information can move. But in addition to this is driven by the speed of sound. Yeah. So the sound wave has to be subtracted here. Yeah. So this is the CFL condition, which is pretty simple. Information can only move delta x in delta t. So this is a very hard limit. Yeah. So then we have a problem of minimal viscosity. Minimal viscosity. So we have the kinematic viscosity defined as nu is our theta, which is the dimensionless temperature, 1 over omega minus 1/2 delta x squared by delta t, and this, what am I doing? This theta here given as 1/3. And of course, omega is our relaxation rate. Okay, now from this we can of course get, so observation would be there is a minimal viscosity that we can put into our method, yeah, or minimal omega until which it will remain stable. So and then yes. So one important thing, this nu, the viscosity. This is of course a physical quantity. Yeah, that's given by your problem. not your choice. Yeah, so this is air or water. Yeah, so but you can still in principle simulate everything with any given omega, provided that you decide on a particular resolution in space and time. Yeah, so you can, because you can solve this for delta x square in this sense. This is your viscosity times delta t divided by theta 1 over omega minus 1/2. So given a viscosity and given a delta t, yeah, we can choose a delta x by varying omega. Yeah. So, and what else do we have in the simulation? So we have a velocity, a given velocity u, yeah, and this velocity u can also be written as the Mach number divided by the speed of sound, which is, I remind you, the square root of theta times dx divided by dt. Okay, so this is kind of a transformation here. You have a physical velocity that you want to adjust, yeah? So Mach number, in diffusive scaling at least, is a variable parameter, yeah, that you can choose. So you can choose your Mach number. This thing here is fixed. And yeah, now this obviously places, so when you have a given Mach number and you have a given velocity in your physical problem, then you could solve this here again for delta x, given a velocity, given a time step t, that would result in this delta x. Yeah. So, or the other way around, you get a delta t. If you solve this for delta t, you get Mach number divided by square root of theta divided by your physical velocity times delta x. Yeah? So, saying, given you have a velocity u, you choose a Mach number Mach, and you already have a delta x, then this will be your delta t. Yeah? So, and now what we are going to do now is to combine these things here. So I will put this here into this here, in order to see that we have delta x square is nu times the Mach number times delta x divided by, okay, now we have to combine these things. I guess this will be 3 theta to the power of 3/2 times u times 1 over omega minus 1/2. So now we have delta x on both sides, so we can simplify this to delta x is equal to nu, the Mach number, divided by theta 3/2 u 1 over omega minus 1/2. Okay, now there are 2 parameters that we can choose here. So nu and u are physical parameters. The Mach number in a compressible flow is also a given parameter. Yeah. So you have to decide whether you study a compressible or non-compressible flow. So yeah, suppose you want to have a non-compressible flow, then of course you have some choice here, but the other choice that you have anyway is the omega that you can choose. Yeah. So having all of that, let's look at our cost, because this is what we are interested in. So the cost is volume times duration divided by p delta x cube delta t. Yeah, and now we have these things here. We have delta t here, and we have delta x here, and now we plug them into this equation. Okay, let's wait. We should first plug, because this delta t still has a delta x in it. Now I enter this guy again here, and then I have delta x by itself, delta t by itself, right? So this will give me hopefully new Mach number square, and this times this gives theta square u square, and here we have 1 over omega minus 1/2. So right, now we have delta t and we have delta x, yeah? And these two things we can introduce in our cost function. So let's put this in the cost function. We have the volume times the duration. These are physical parameters, not our choice. The performance of our code, well, this is given by the computer and how well we programmed things. And now we have to take delta x to the cube. Mach number theta 3 u 1 over omega minus 1/2. So all of this goes to the cube. And then we have here Mach number square, theta square u square 1 over omega minus 1/2. Okay, so and if I'm not completely mistaken, this goes to volume times duration times, okay, we'll pick these two things here up, omega 1 over omega minus 1/2 to the fourth power times u, so u to the comes to the third power here, to the second power here, so I guess this is u to the fifth power divided by the performance of your code, nu to the fourth power, Mach to the fifth power, and theta to, okay, I pre-computed 13, I don't know whether this is correct, yeah, doesn't really matter, because this is a constant, yeah, so you can absorb this into P or the others. So there are a few things that are constant, V, D, P, and this theta thing, and yeah, U in principle too, but what you see is when you want to run simulations at higher velocities, this is very expensive, yeah, because this goes with the velocity to the fifth power. Also, if you want to have small viscosities, it's also very expensive, yeah. I mean, one thing, okay, if we take these things out that are under our control, I mean, that we can choose independently of what we are solving, yeah, then what we are left is we can choose omega and we can choose Mach, yeah. So we could say of which we control. Yes, you can absolutely make a change by increasing the Mach number of your simulation, yeah? Mach to the power of 5. So you should think about whether you want to have the real Mach number or whether you can trick it a little bit to have a higher Mach number in your simulation than in reality. Okay, so one thing is the Mach number, but the first thing we are dealing with is the omega. What we see is the closer omega is to 2, the lower the cost. I mean, changing the Mach number always comes with some headache. I mean, like, it doesn't feel right, right? Well, omega you can just turn. Yeah, so what you would do is to turn omega. The closer you get omega to 2, the lower your cost. If you set omega to 0, your cost is 0. I mean, according to this equation. Yeah, you know, the problem is accuracy. Yeah, obviously. It's not the only problem with omega. Obviously, you know that there is a stability limit with this omega. There's a stability limit with my computer also. Let's see whether we can solve this. So, let's recall what this is actually doing in the BGK collision operator. So the BGK collision operator looks like this. We have an Fij. Okay, let's do it in 2 dimensions only. Okay, no, we talked 3, so Fijk pre-collision plus omega Fijk equilibrium minus Fijk. So what happens if omega is equal to 2? Then this will simply mean we have 2 times Fijk equilibrium minus Fijk, right? So we have seen this. This omega equal to 2 is the no dissipation limit. Where we have no entropy production and no destruction of information, which is the same. So, what does this mean? There is no destruction of information. You can turn the thing completely around. If there is no entropy, then time is reversible, right? So, as you can see, in this case, Fijk, simply you can put this to the other side and then you get this. This is 2 times Fijk equilibrium minus Fijk post-collision. So you can compute the pre-collision from the post-collision, and it's the same equation. You can just turn it around. Yeah, time is running the opposite direction, nothing happens. So this is perfectly. I mean, you can try out how long this will run. Perfectly reversible. So our observation was that BGK, we did not observe this because, but we actually were able to set it, I believe, to 1.95 in the example that we had, and we tried this out before. So if you get it a little bit larger, then it will crash. But it can also crash at, I mean, this was this particular example. There it got a little higher, yeah, but usually if it's larger than 1.9, it often crashes. So there obviously is a limit. And the solution to this, that people have yeah, the solution to getting lattice Boltzmann more efficient is to get omega closer to 2 without losing stability. And today we see one way how this historically has been attempted and was partly successful. Okay, let's dive into the theory again. So, very central lecture was lecture 6, where we had this asymptotic analysis. We'll always return to this. So in lecture 6, there we had equation 6.6.6. This was a 2D lattice Boltzmann equation that we analyzed for the Navier-Stokes, so leading to Navier-Stokes equation. And with this we mean the momentum. Equation. So, and this momentum equation looked like this. We have a time derivative of m10, so we are now in 2 dimensions, to the first order plus dx m20 to the second order plus dy m11 to the second order minus omega 10, this is the forcing term, to the third order. Okay, let's today just assume that there is no forcing, because this is not helpful for us now. So we have in this that m10 to the first order is the momentum, rho to the 0 order times the velocity to the first order, and m20 to the second order is being equal to the m20, what am I doing? Not this, equilibrium to the second order minus, here we have this 1 over omega minus 1/2, and here we have the large omega to 0 to the second order, and we have m11 to the second order is m11 equilibrium to the second order minus 1 over omega minus 1/2 omega 11 second order. So why am I reminding you of this? The thing is, we choose for the BGK this omega in order to get the this Navier-Stokes equation correctly. And for this, we used an omega that we apply to all the populations. However, as we see from the asymptotic expansion, this omega is relevant only in the second moment. Yeah? So it does not, the other moments do not appear with here, so it is not necessary from this equation to fulfill this equation that they have the same omega. Yeah? So this is only second moments. So it is only required to do this for second moments. However, BGK does it for all the moments together. It acts on all moments. So the idea of the classical MRT method is now the following. We could use different relaxation rates for different moments. with different rates. Okay. And for this, we have to start with, okay, let's look at the two that we actually have to take care of. These are these two here, right? Yeah, so we have to look into what is actually this omega here. So this omega to the second order, omega 1, 1 to the second order, there are these derivatives, dx uy first order rho to the zero order plus dy ux to the first order rho to the zero order. Okay? So this is something that shows up in the Navier-Stokes equation on the diffusion part. And let's look at this omega 2, 2 to second order. What we have here is dx ux first order rho zero order plus theta dy uy first order rho zero order. Okay, so if you don't remember these equations, you have to go back to lecture 6. Yeah, so this is where they come from. Okay, so what we have in here is something that looks like a divergence but of the velocity, but it is not a divergence because the theta is not equal to 1. Yeah, but you can imagine if you now add omega 2, 0 to second order plus omega 0, 2 to second order, you actually get a divergence. And this will then look like this. So you have 1 plus theta. So I hope these are all right because I'm now just writing them from the script. dx ux to first order plus dy uy to first order. And now you have to remember that to first order, and these are to first order, yeah, the divergence has been identified to be 0.
Because it's incompressible.
No, because because in diffusive scaling we get the incompressible Navier-Stokes equation out. Yeah, so this is actually a result of that it is incompressible is a result of the asymptotic analysis in diffusive scaling. So this here is 0. Since it is 0, it doesn't matter how you relax it. Yeah. So remember, you add this to 1 over omega minus 1/2.
Yes.
Yeah. So then, if you multiply 0 by this, then it doesn't matter. However, it matters because you don't have this guy, you have this guy here, which is not the divergence. So now you have to make your first trick. Okay, let us note this down. So relaxation of omega 0, 2 plus omega 2, 0 does not show up in leading order Navier-Stokes. Okay, so we can take this thing out. However, since we are interested in omega, not omega 2, 0, and not in the sums, so we also have to deal with the opposite guy, this omega 2, 0 to second. The opposite will be the difference, obviously. Yeah. So if you have the difference and the sum, you can get the two of them out, right? So, and this is 1 plus theta rho 0 and here you have dx, dxu, wait, am I doing the right thing? Yes. X first order minus dy u y first order. So I'm just, okay, lecture is never completely out of mistakes. I'm writing it from the script. Maybe there's a small mistake, but wouldn't matter. Now, the only thing that matters is we split it up in the sum and the difference, okay? So, because this guy still is important. So the relaxation of the difference is of influence to leading order. So here we have to use our BGK collision frequency. So what we do is we do a regrouping. So we say we have the moments together M20 plus M02, and this is something that can relax with something else. So we give this a relaxation rate omega p. And the other thing, M20 minus M02, this gives the omega of the BGK. Yeah? Now, let's look at all the moments in our two-dimensional example. In 2D2Q9. So what moments are here available? We have moments M00, M10, M01. So these are conserved moments. Yeah? So no relaxation here. Then we have M11 and we have M20 minus M02. These are the so-called non-conserved hydrodynamic. Oops. So these get relaxed with omega BGK. Yeah, so but they would be the usual ones. Then we have this guy here, M20 plus M02. This actually is the pressure, or we call it also the acoustic moment. And this we relax with omega p, which then in literature will be related to what they call bulk viscosity. Bulk viscosity is not a very well-defined quantity, and this can be used for the damping of sound waves. So now we have 6 out of 9, means we have 3 more, and the 3 more that we have is M21 and M12. These are third order. we give for the third order, we now, without much explanation, we give an omega 3, and then we have 1 M2 2. This is the fourth order, and without much explanation, we present an omega 4. So these here are the ghost moments. So the idea, one idea in order for stability is that by choosing omega p in a value that is independent of viscosity, we can suppress pressure waves. And there's an assumption, there's a strong assumption that pressure waves are the reason that Lattice Boltzmann BGK becomes unstable. I am personally a little bit of the opinion that this, even though it's a strong belief that you read a lot in literature, it hasn't really convincingly been shown, at least not to me, that this is the main reason. Yeah, but okay, anyway. Yeah, you could have the idea that you want to suppress pressure waves. So, first of all, if you want to okay, so the reason why some people don't like these multiple relaxation time approaches, or what, you know, you always have to, in science is a bad science in, yeah, is a bad business where you always have to, you know, you have your own idea and then you always have to say, so the idea of the other guy is a bad idea, so which I obviously do myself, as you have noticed in this lecture. Yeah, and so if you have a different idea than MRT, then you can trash MRT by saying, oh, they are just increasing the bulk viscosity and this makes them stable, and then you have no chance of doing acoustics with this because you artificially increase the damping of acoustic waves. Yeah? So then people who want to do acoustics with Lattice Boltzmann, they say, no way, we are not interested in this. So, but suppose you're not doing acoustics. If we do acoustics, then we have to talk again. And again, I'm not absolutely convinced, yeah, that this is not, you know, this is kind of a little bit of marketing from the other side, if you will. So you're not interested in acoustics, then, I mean, if you are interested in acoustics, then you are not allowed to use diffusive scaling anyway, right? Then you have in a different game. So now you're not interested in the acoustics, so you use diffusive scaling. So delta T is proportional to delta X square. I hope everybody knows what acoustic scaling is by now. The speed of sound, Cs, is the square root of theta delta X by delta T. Yeah, so it's, of course, this is 1/3 delta X by delta T. Now you can introduce an artificial Mach number, which of course you're only allowed if you're not interested in acoustics again, yeah, because then waves don't move with the right velocity. Artificial Mach number. So say we have the limit of delta T going to 0. Mach is the limit of delta T to 0, U divided by Cs. This will then go to 0, yeah? Yeah, so in acoustic scaling, your Mach number is, if you make your crit smaller, then automatically your Mach number goes to 0. In this thing, I mean, if you have not infinitely short time steps, as this actually means, then you have, of course, reminders of this, and this is regarded as noise. Okay, it's a little bit stupid, yeah? So pressure waves in air are regarded as noise. Ha, 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 ha. Noise meaning you don't want them. I mean, try to explain. Try to explain to somebody who is they are so strong believers in incompressible, fluid dynamics. You know, it's very hard to argue with these guys. You know why it's hard to argue with these guys? They don't believe in pressure waves, so you cannot talk to them, right? Okay, sorry. Omega p. When we put omega p, something like close to 1 or at 1, yeah, so this will quickly damp acoustic waves, and then your noise is hopefully gone. So, and the idea behind this is that this is a way of improving stability. I mean, it certainly improves stability, but I'm not completely sure that this is the main thing in that we are really seeing. Okay, so we can get rid of the pressure, and what we also want to get rid of is the ghosts. Okay, what are the ghosts again? Ghost moments M21, M12, and M22. So these guys have no effect on the leading order. This is why we call them ghosts. So here again, we could have the idea, which, I mean, this is a classical idea that people have. I'm trying not to imply that this is the best solution. Yeah, it's just, you have to study these things a little bit harder in order to get to really see what is really happening. Yeah, but let's say we could have the idea that we suppress these things by increasing their diffusion by putting these values again close to 1. I mean, away from 2, and also away from 0, usually. Yeah? So, that's part of the idea, and then there is a little bit an addition that we come to in a minute. Yeah, so this leads us to the classical MRT model. And with all of these things, I have to tell you this is kind of debunked in a okay, it's not completely state of the art, let's say, yeah. But is important to know it, is also important to know what is the limitations, which we'll come to in the session after the lecture, in the coding session. So this is from, okay, so the model is actually, I believe, a little bit older, but in this publication you can actually, the derivation is in Physical Review E61, 61.6. Luo is Pierre Lamont and Li Shi Lu. So let's talk about how it's classically done. And this is not the way we do it today, but it's important to know. So there is a transformation done between the distribution, so the populations, the sum of the populations, and the moments. And this is done by using a matrix. And you know, especially if you come from solid mechanics, there are people in numerics that to which you cannot talk if you are not talking with matrices, right? Yeah. So for some people, a matrix is a given. So you cannot talk without a matrix. So they love this kind of thing. You get the moments. You get a vector of moments by multiplying a matrix to a vector of populations. Yeah? So this is a moment vector, and there is a population vector. So, of course, this leads to this classical notation that we already had in a little bit different form. So there's a vector notation. Yeah, you remember we had this also as pras and cats. Yeah, now here it's also given as fi. So there is one index. So we'll often see in the literature this written with one index. In particular with the classical guys. These guys who are now in their, between their 60s and their 90s, in between this, yeah, these scientists currently, they insist still on this notation, and of course all their offspring probably too. And then there is, you have to compare this with Miller indices that we are using here. I'm such a bad guy. I'm always trying to bash somebody. Yeah, Fij. So Fij. So we have one index per direction. This is we do not like matrices, because when we have a matrix, we have an ordering. This ordering is arbitrary. Yeah. So this here is something that you don't need to know anything. Yeah. The others, so the guys who are using the matrix, they also don't need to know, because they say this is a matrix, and if I want to know what is inside, I look it up. Yeah. So we say we don't need to know because we can easily generate it. Yeah, from scratch all the time, and we don't need to look something up. I find this is much better. That's, you know, you can always generate it without looking anything up. So this ij then is, in our notation, is different. This goes from -1, 0, and 1. So okay, so this is something you have to live with, because you are hearing the lecture from me and not from the French guys, yeah, who would always do it this way. So, being in this original Pierre Lallemand version, the collision looks like this. So you have an M after the collision is M before the collision plus a collision matrix. Here comes a vector of equilibrium moments minus M, the incoming moment, and this vector with the relaxation rates is a diagonal matrix. So sometimes I sometimes get a paper where somebody says, "Oh, I have made an interesting discovery. We could also have this matrix in a non-diagonal fashion." Yeah, and this is great, but this just is a redefinition of the moments. Yeah, so that's what is considered here to be a diagonal matrix, of course, depends on how you define your moments in your matrix. Yeah, so this is a diagonal relaxation matrix where in the intros we have per moment it's the relaxation rate for that particular moment, right? So, once we have done this collision, we have the back transform. We have the back transform, then we have F after collision is equal to the matrix minus 1, so the inverse of that matrix. Now the matrix has you, and then we have the post-collision part, and once we have the post-collision part, we can do the streaming. So streaming Fix plus Ex, so the vector in that particular direction, t plus delta t, is equal to the post-collision x and t. So, by the way, is this push or pull? This is push, right? Yeah. So this is the way we also wrote it in the code. Yeah. So we could also write it the other way around. We could here minus e minus ei and minus t minus delta t. Yeah. Then it would be a pull. Okay, so how are these two methods different? So we have MRT, multiple relaxation time. So it's streaming the populations, and it collides moments. And BGK was you stream populations and you collide populations. So you have an additional transformation in this. Now we have not talked about this matrix. And this is where actually problems are hidden. And part of them, they are actually pretty well hidden. Okay, classical MRT uses an orthogonal matrix. So they somehow insisted, yeah, so these guys like matrices, and now they're interested in the property of their matrix, yeah? So, and then they ask, is my matrix orthogonal? And if you put the moments as the moments we define in countable fashion, by the way, which is an idea that they didn't have anyway, so they had to think up their moments somehow, because they just didn't have the idea of counting them upward. So they somehow had to decide on moments from wherever, yeah? So, and then they found, okay, let's have 9 different definitions of moments somehow, and put them into a matrix. And then what properties does this matrix have? Well, we should make them orthogonal. By the way, they are not also normal. They don't want to have them also normal, because if they would be also normal, then they would have fractions in the matrix. Yeah, so they thought a little bit about the numerics, that they don't want to multiply with fractions, because this creates your numerics. They want to have integers in the matrix. So you multiply this by, so you're not doing it, you're not normalizing them, or you multiply them with a higher value, so that you get this orthonormal but non-orthonormal matrix with all integers in it. Okay, so another thing is, of course, now they sort these things up all one moment at a time. I mean, this is, of course, you first have to, they were the first doing this, yes? There was no instructions, yeah? So you have to use any specific ordering of your populations in the matrix. So, because they were not using countable moments. Okay, let's have a look what they came up with. D2Q9 moment system by Lallemande. I believe it's from Lallemande, but the publication is, of course, from both of them. Lallemande, it has the same age as my father, I noticed. M. So So the list of 9 moments is, there's a moment rho, there's a moment called E, there's a moment called epsilon, there's a moment called Jx, there's a moment called Qx, there's a moment Jx, there's a moment Qy, and there is a moment Pxx, and there's a moment Pxy. And I have absolutely no idea how they either get to this ordering nor to these names. Okay, anyway. So they decided that these are the moments. And for me to actually comprehend this, and probably because I taught you, it may also be easier for you, we have to translate this into countable moments. So what is this in terms of countable moments? So rho is what you expect it to be. It's M00. Yeah, this is one of the conserved guys. I like to put I like to order things by order of moments. This is not what is done here. So this is the zero moment, obviously. The next thing, E, is not the first moment, it's the third, is the second moment. It's made orthogonal, so it's not, it looks a little bit strange. It's 3 times M20 plus M02, yeah, so that would be a second moment, obviously, but it's not a second moment, it's a orthogonalized second moment, it's minus M4M22. So, not countable also means they are mixed, there's a mix between moments of different order, yeah? And this is supposed to be related to the acoustic. Okay, so then epsilon. Any idea what epsilon could be?
I think it could be, probably the momentum could be like 1, 0 plus 1, 0, 1, or maybe...
No, that doesn't make sense physically.
Okay, then it would be...
This would be a velocity in the diagonal.
The epsilon.
No, if you the thing that you just mentioned.
1, 0, and 0, 1, okay.
Yeah, so this would be a velocity in the diagonal. This is like you're turning your coordinate system. Well, this thing is a ghost. This is a ghost moment. It's a combination of the zero moment, 4 times the zero moment, minus 6 times the pressure, plus 3 times this forced moment, and this here is considered to be a ghost moment. Okay, now combination of 3 different orders. Momentum, you were speaking about momentum. Finally, we get to the momentum. Jx is M10, and this is conserved, where I always assume here there is no force. So some of the conclusions of today are only valid if there is no force. Yeah? I don't want to dig into this today. So then they are not continuing with the velocity in x, but they start with y, but they have here this qx is 3 times m1 2 minus 2 times m10, and this is also considered to be a ghost. Then jy is m01, so this is the momentum. Conserved, and then they have, of course, this q, qy, so which is again 3 times m21 minus 201 ghost. If you feel this is torture, this is torture. Yeah, pxx is, okay, now comes these guys. Pxx is m20 minus m02, and pxy is m11. Yeah, so these are the hydrodynamic. Okay, so interesting is that the important stuff, if you will, say the thing we are caring about. No, don't use this color. The things we are caring about, yeah. Rho, yeah, the momenta, and here these second moments. These things are the same as if we had them countable. Yeah. What is different is the ghosts. They are kind of mixed up. So, why do they look like this? So these moments are chosen to be orthogonal with respect to the unweighted scalar product say we have a moment m phi. So, I mean, we've already done this, but I remind you. So, if we now in my nomenclature with two indices, we have a kernel phi ij over fij, and we have another moment m psi, which is the sum over ij. What am I doing here? Ij. Yes, so we have this kernel psi ij into fij. Yeah, so then the unweighted orthogonality means, so these, the m phi and m psi are unweighted orthogonal if the sum over ij phi ij times psi ij, if this is equal to 0. So this is what they did in order to get this 0. Basically what they did is they used Kram-Schmidt's orthogonalization on the matrix, because they are people who were told in school that it is nice that your matrix is orthogonal. It is, I mean, it is really, 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 really difficult to get a reason out of this guy, out of these guys, why they did it. But many of them are still very, very, very convinced that this is that you have to do it this way, yeah, because you know the inventors of this did it this way. Come to hopefully we'll come to the problems that this causes later, I mean, in particular next week. So, example, E. Try to understand this. So we have E. E is equal to yes. So E is equal to M20 plus M02. So remember, the countable moments are not orthogonal to each other, right?
The countable, yes,
They are not. They're not made orthogonal. So you can write these things here now as ij going from -1 to 1, fij. So the kernels are here. So for this here is I to the I square plus j square, and the kernel for M00 is 1, so this will be just 4, right? So this is the kernel for this moment. And so, yeah, you could say that phi ij in this kernel would be 3 times I square plus j square minus 4. And if we look at rho is equal I j minus 1 to 1 fij, so the kernel is just 1, so this means that psi ij is equal to 1. So now you can check this by doing that j from -1 to 1 over phi ij times psi ij. So psi ij is simple because it's 1. Looks like this. So you have 3 times I square plus j square minus 4, and this times 1 because the other one is just 1. Now you can do all of this, then you get 3 times 6 plus 6 minus 4 times 9, and this is equal to 0. So we are successful, yeah, in showing that these two vectors are unweighted orthogonal. So, as you hear from my tone, there is, of course, not a very good reason to do this in the first place. Orthogonality was assumed to be important. Let's say based on a misunderstanding, and it's not clear what this misunderstanding was, but I regard this as a lesson for science. You see, if you believe in something very strongly, but you never really formulate what that particular thing is really necessary for, then you can never be proven wrong, because this is not a testable hypothesis, yeah. And since it is not a testable hypothesis, it will stay there forever, yeah. Because if you read the book, say the other book, because they don't care about this in the book that you like, yeah. But you learned this from Lallemant himself. Yeah, and you were a student of Li Shilu, and this is, they taught you this thing, and now you come to me. I mean, this happened to me a lot of times, and I say, so orthogonality doesn't do what it's supposed to do, and now you demand from me, that I prove that it does not do what it's supposed to do, but you're not telling me what it's supposed to do. Yeah? So how should I show you? Okay? So it's a bit of an uphill battle. However, we can actually say that in the meantime it has been pretty settled. No, this doesn't work. I mean, it does, okay, we'll see how it works, okay? Let's first go to the question whether orthogonality matters. Now, you poor guys who have to suffer from, this discussion that happened before you came to Lattice Boltzmann. Okay, anyway, does orthogonality matter? So what is the right answer for this? The right answer is sometimes. It makes a difference, okay? What difference does it do? Sometimes. Oftentimes it does not. So let's look at, what's the time? Okay, let's look at the third order moments and see whether it makes a difference here or not. So the third order moment is here called Q. Yeah, Qx. Qx post collision would be qx before collision plus omega 5, because it's the fifth moment in their list, into qx equilibrium minus qx before collision. Okay? So is this giving us any different answer, is the question, then if we relax the countable moment? That's the question, because if they give the same answer, then there is no reason to make this orthogonal. Yeah? So let's have a look what this actually means by writing it in terms of countable moments. So you can write it in terms of countable moments, saying that this is 3 times 1 moment m12 minus 2 times the moment m10. And this for the pre-collision is the same. So here comes the pre-collision, 2 minus 2 m1 plus, now comes omega 2. Here comes the equilibrium of these guys, 1, 2 equilibrium minus m10 equilibrium minus again the pre-collision part. So the 3 times m12 plus 2 times m10. So now comes a speciality here, namely that m10, this is the other guy showing up here. This is a conserved moment. Because it's a conserved moment, pre and post collision is the same, and is also the same as the equilibrium. Yeah, because they are conserved. So, if they are conserved, what you recognize very easily is you have the same guy here as you have here. You have the same guy here. Oh, no, you don't, because there's a 2 missing. Yeah? So you have the same guy here as you have here. Yeah? So they will all eliminate each other. Yeah? And all you are left with is that you are not relaxing the third moment, but you are relaxing 3 times the third moment. Yeah? So, but even you can divide the entire thing by 3 and you end up with exactly the same. Yeah? So, basically, this is m12 is equal to m12 plus omega m12 equilibrium minus m12. Yeah? So, if somebody tells you, make the mass, then you will see there's a difference. You see, there's no difference. But there's a special case. What is special at this case?
That you have the omega or each omega, or 1 omega, would that be something that differs? That you have
Oh wait, did I have to put 5? No, the special case was that the thing we made it orthogonal to is conserved.
Okay.
Yeah? So let's. Okay, so this is we have to look at a different example. Same as if relaxing raw countable moments. So this particular velocity set is a very special case for lattice Boltzmann in as far as there is only one moment, only one ghost moment that is not automatically that's not automatically orthogonal to any of the other. Okay, I have to reframe this in a different way. So this, what we saw here, where there is only one non-conserved moment in this definition. This shows up only for one moment in this on this lattice. However, this is a special case. On other lattices, there are many of them. Here is only one. Okay? So this model, this 2D model, which is very successful and works very well, comes with the caveat that the theory that they applied, would apply only, would make a difference only in one moment only. And this one moment only is the forced moment, the one with the least effect. Yeah? So let's look at this one moment in time. So let's have equation 9. I know I'm already over time and we still have to go for the exercise session. So if anybody disappears, so they just disappear as you wish. Yeah? But it will be interesting and you will learn something. So epsilon, yes, epsilon is the only guy that is for this two matters, and this is the third one. So this goes epsilon equilibrium minus epsilon. Okay, so when we plug everything in here, so and this is ugly, it's 4 times m00. So this is conserved. We don't we don't care about this. 6m2 plus m02. So this is not conserved. This is the problem. Then we have m22 after collision is equal to 4 times m00 before collision minus 6m20 before collision plus m02 before collision plus 3 times m22. Now comes the collision part plus omega 3, 4 times m00 equilibrium minus 6 m20 equilibrium plus m02 equilibrium plus 3 times m22 equilibrium minus all of the same 0 plus 6 m20 plus m02 plus minus 3 m22. Okay, so we do not care about this guy because this guy is conserved. Yeah, so they are all the same. Yeah. However, one thing we are caring about is, say, no, it's not 8, it's 9.2. So we have m20 after collision plus m02 after collision is m20 plus m02. And this comes with omega 2. Omega 2 m20 equilibrium plus m02 equilibrium minus m20 minus m02. Yeah, so this thing is not conserved. Now we plug this into the previous equation, so into 9.1, and solve this. We plug it in and just resolve this for m22 after collision is equal to m22 before collision plus omega 3 m22 equilibrium minus m22 before collision minus, now comes something strange, 2 times omega 3 minus omega 2, times, okay, it doesn't fit here, m20 equilibrium plus m02 equilibrium minus m20 minus m02. Okay? So, For this guy, we have something that kind of depends on two relaxation rates. Yeah? However, the difference, I mean, orthogonality, the idea, the rough idea behind orthogonality is to make moments independent of each other. Now, these guys would be independent of each other if their relaxation rate was the same. Yeah, so, this appears when their relaxation rate is the same. Otherwise, they are somehow, there's something strange going on, which is difficult to see from this here alone. So, we get a composition. They influence the relaxation process if omega 3 is not equal to omega 2. By the way, in BGK you don't care because this is BGK. BGK has omega 3 equal to omega 2. All omegas are the same. The exercise was to get them independent of each other. Yeah? This was our goal. So something is strange here. And if you bear with me, I mean, if you have any other constraints, now you can, of course, run away, but I'll, so today we'll make an exercise session right after this here, where we actually see in practice, hopefully, that this makes a difference. So, but the lecture is now over. Do you have any questions? I will keep the recording on because we'll just jump into the result, into the session. Oh, this looks frozen. Do you still hear me?
Yeah, we do, but it's frozen.
Okay, so but only my picture is frozen, right? Okay. Let me see. Does it? Oh, yeah. So it does. It's still okay. No, this is the wrong one. Okay. Don't mind my face is frozen. Doesn't matter. What am I doing?
Then I have a question.
You have a question.
By applying Kram-Schmidt or orthogonalizing these matrices, they found like a combination of these moments which can make the simulation more stable, right? Or that suppresses the.
No, they with Kram-Schmidt they found moments that are orthogonal to each other, and for most of them that's so. The only moment for which this makes any difference is epsilon. Yeah.
Okay.
So now the idea. Okay, you remember our code from last time. This is the code from last time.
Yes.
No, the idea that I had is okay. I have to change the system a bit. So the idea that I had is that in this code we will now simply, so we have this function run, which is the BGK function. So my idea was I will take this function run and just copy it. Okay, yeah, so I'll copy this entire function, put it here, where is this not, okay, I put it here, and then I will rename the copy as run MRT, yeah? So, and because we don't have specific variables for the other relaxation rates, I will now introduce here additional parameters, yeah, so that we can run this with the different rates. And the first I introduce is the one for the what they call E, yeah. I call this actually the pressure, and I call this for this omega p, and I will call the numbers are now a little bit different, yeah. So I will introduce an omega for the third order moments and one for the fourth order moment, right? So, and then
Would it be needed to use Mathematica, or it can be done from here just to run these?
okay, maybe we'll use a little bit of Mathematica here, yeah? So, because we have to do some work, of course, yeah? So, what we still need is the velocity. We do not need these things here. Well, I will delete them later. What we do need is first to compute the moments. Yeah? So the moments I will start. Okay, let's have this as an exercise. We have I copy the zero moment, and now we'll have local variables. So we need what moments do we need? We need the moment m20, for example. Yeah. So m20, how is m20 combined? So it's where the first index to the power of 2 is 1.
Yes.
Yeah. So the first index. So the first index, when the first index is 0, and you put this to the power of 2, you get 0, right? So then this will mean everything that has a 0 here will disappear, right?
Okay.
Yeah. So then this, you see, here we have p. So when we have p or m, yeah, is 1 or minus 1. So put to the power of 2 will all get the same, right? So this means we have just to delete everything that comes here with a 0 in the first entrance.
Okay.
So this gives us this second moment, okay? Let's do the other second moment.
I have here a question, because we have in the notes we have one definition of the moment in terms of the meter indices. Our
Yeah.
was I squared, so it's. Do you think you could write again is there like a way to just so that I can see the.
You want me to write something? What do you want me to write?
It's just the moments in terms of these Miller indices, or I plus J for the D2, Q9. I don't know if.
You mean MAB is equal to the sum over I, J, and J from -1 to 1, I by the power of A, J by the power of B, and this into Fij.
Okay, yes, thank you.
Yeah?
Yep.
Okay, so this is what we are doing. Now, it's an exercise. Okay, some people are still following. So, but we need concentration today because we want that this runs. And if we make one small mistake, it will not run, okay? So now try not to disturb me too much and try to follow what we are doing. Now, we did this for the for M20, now we have to do it for M02. Here again, this thing in front will disappear. Now everything has to disappear that has a 0 in the second index, right? So basically this will look like this. Okay, so now we have these 2 second moments. Now I always start from the full thing. I get the next thing we need is this M11. Yeah, please, everybody is looking. What am I doing? So if you think, so this is I by the power of 1, J by the power of 1. Yeah. So this will be positive if they both have the same. So if one of them is 0, they disappear. Right. So then this here will disappear. This here has one of them 0. This will disappear. And the other thing this also has one of them 0. They will also disappear. Okay?
They are related. Yeah, now to the.
Okay, so now I times J is positive if I and J are both positive or I and J are both negative. Yeah? So this would mean here they are, oops, what did I do? Here they are both positive and here they are both negative. So here they are the opposite. Okay, let's do it this way. Let's do it this way. Okay, so now we have the second moments done. Now for a third moment. Third moment. Float M21. Okay, so now this will, if any of the indices is 0, this will be 0, this will disappear, yeah? And it will be positive if the last index is positive, and negative if the last index is negative. Okay? So any of them 0, gone. Yeah, any of them 0 gone. So this is here, all of them are gone because they have some zeros in it. So, and now the last index, if this is positive, it is positive. So here it's negative. If the last index is positive, it's positive. And then this is negative like this, okay? So it's not so difficult if you use countable moments. You see, we don't need to look into the matrix. We just know, yeah? Just looking at it, you know. Just look, no, yeah? By the way, this is, if you ever have if you see Li Shilu, this is the way he is talking. And he's saying something different. He likes matrix. So, float M12. So the same thing should look. So everything with 0 disappears. So where's this bracket here? So everything that has the first index positive is positive. Yeah. So this one, the first index negative is negative. First index is okay. It's ugly, but let's do it this way. Okay. Doesn't could have this more. Yeah. Okay. Let's just do it this way. It doesn't look nice. If you do it right, you'll do it in a different way. Okay, so last one more is M22. So what is M22? Everything that has a 0 will disappear. Everything that has no zeros will just be positive, right? So it will just disappear. And these disappear, and that's what's left. And this is how you compute countable moments. Oh, so easy. Okay, so I want to simplify our life a little bit here by so I proved to you that the orthogonality of the third order moments does not matter. This is why I don't want to spend time on this, and we only care about the guys. We only care about the guys where it matters now. Yeah. So we'll compute epsilon. This is obviously where it matters. Epsilon. So epsilon has been defined as, you look in your lecture, as 4 times rho x and y. So this is the one moment that we put actually inside the matrix, because we did not compute it as in a local variable. That's why I have to write it like that. Minus 6 times m. So you're following whether I do this correct? Yeah. 6 times m20 plus m02. So what else?
The thing is, I see a minus. I don't know if I'm seeing the right one, but I'm seeing a minus 4 times rho.
Minus 4 times rho. So where are you seeing the minus 4 times rho? Okay, let's go to the lecture. Wait. We have to see in the lecture. So you see minus. Where is this minus? So it's 4 times m00 minus 6 m20, and here plus 3. Okay, so this is how these guys defined it. Where is my code? Here. So this means I have a memory like a goldfish. Plus 3 times m22. Go. Now we have our epsilon. Now we also want to have our E. E is 3 times, right? See in the notes, 3 times m20 plus m02. You agree?
Yes.
Now you see, I see where you have your minus. Minus 4 times, so this is rho, the zero moment, x and y. Okay? So now we have defined these, and we also have to have this other guy that they call pxx, which is the difference, m20 minus m02. Okay. So then instead of doing the collision with BGK, what we are now doing is collision with moments. Yeah, so what is basically is the same equation. It's m11. M11 is m11 plus now the usual omega, because this is the hydrodynamic moment, right? Omega times, so now comes the equilibrium. Okay, we have to specify the equilibrium here. What is the equilibrium of M11? Rho, right, so it's rho x, y times ux in x, and so, no, I'm always making this wrong, and y times uy, x, and y. So this is their equilibrium, and from this we have to subtract M11 pre-collision, right? So this is how we do this guy. So then next, the other hydrodynamic moment is this pxx. So by the way, I'm now just overwriting. I'm just now overwriting stuff. Yeah? Yeah, so I overwrite these moments into itself because I'm not using them later anymore other than for, I don't need the pre-collision anymore afterwards. Pxx, so P, this means Pxx before collision plus omega is the same omega because it's a hydrodynamic moment. So now we have to know what is Pxx and what is their equilibrium. I believe it will start with rho, right?
Yes, to 0 would be rho times ux.
So it will be ux, x, y, so
Plus 1, well, the speed of sound squared, which is 1 over 3.
okay. Is it ux or is it, I mean, there's a second moment. It must be, it must be a square of a velocity.
Yes, ux squared.
So it's ux squared, yeah? Ux squared. Is everybody still following me? Ux, so now you said something about 1/3.
Yes,
So do we need this? Remember, we are talking about M20 minus M02.
no, because it comes.
Yeah, so this will cancel out. So what we are left with is ux square minus uy square. So this is our equilibrium. Okay, so what's about the brackets? Here, minus, or always watch out that I don't make any mistakes, minus xx. So, now we are done with our hydrodynamic moments. What's next? So let's do the acoustic moment. E is E plus, now this comes with omega, with p. Yeah? We are talking about, yeah, so different, this is what we wanted to do, different relaxation rates. So now we need to know what the equilibrium for this is. And now it is of course helpful that you know that there was this 1/3, right? Yeah? So, because, okay, again we have rho, x and y. And now you said 1/3. Now, it's the 1/3 and the other one is 1/3. Yes, so it's two, I think it's 2/3 plus, okay, I take the liberty of taking this thing here, yeah? And take a plus here. And I made a mistake. Do you see? Wait. Okay, why is this a mistake? Because this is actually not like this. It is this here. Okay, remember there's a 3 here, right?
Yes.
So we'll have to multiply this entire thing 3 times, so yeah, 3 times this, and then comes rho, then I made -4 because the rho is already there, right? So this is the strange equilibrium that we have to deal with. And then minus E. Okay? By the way, if we did not use this in an orthogonal form, we would have to type less. Yeah? So everything that we have to do here, we have to do here again. Obviously, if we didn't do it here, we didn't need to do it here. Yeah? It would be more efficient, less round off, doing the same. Yeah? Okay, anyway, this is how it's defined. So, then we come to the third order moments where we just you know, do it, not thinking about. M to 1 is M to 1 plus ohm 3 times, so what is the, they all start with rho, right? X, Y. So does anybody out of the internet can tell me what's the equilibrium of this third order moment? This will be on the test. I heard something and then you disappeared again.
It's just that I don't have access to the node, so I can't.
Okay, no access to the node. So you should, the thing that you should remember is you can generate the equilibrium of a moment by taking the product of the individual moments. Yeah? So it's the one for M10 times the one for M02. Yeah? And as you have to divide by rho. So the one for M10 is obviously UX X, Y, and the one for 02 is what we just had. Yeah, this is 1/3 plus UY X, Y times itself. So this is the equilibrium for that moment, right? Minus M12 semicolon. I hope this was right. Then we'll do it for the other one like this. We just exchange the indices here, here, and here. And of course here. Okay, still everything nice? So let's have the last guy. So this is now ugly, epsilon. Epsilon. Epsilon is equal to epsilon plus ohm 4 times. Oh my God. So it will be, the one thing that is clear is it will always be proportional to rho. So this is something that we can write out here. So what is this? So we need, okay, so we can start with the 4. Right, so we start with the 4. So then minus 6 times, okay, by the way, 6 times this, right? Will be 6 times this. So I'll take the liberty of just copying this. And something is missing. So, yeah, the 3 times, okay, plus 3 times, so ugly, 3 times. So we need the second one. So basically this is the second one, yeah, in one direction, and this is it in the other direction. So I'll take the liberty of taking this here and multiplying this with this here, hoping that they have been correct before. Okay? So now from this I subtract epsilon, and then I'm done with my collision. Great, without using Mathematica. Huh? Okay, hopefully that we don't know whether it's correct. So these, okay, this is something that we don't need. Okay, we need something else. We need something else, and the thing that we need is we need to compute the post-collision moments. So we, okay, so in order to first, right, so we have this moment epsilon E and Pxx. Yeah? So for this, we want to still have the post-collision moments. So we need the moment post-collision moments. So the post-collision moments, so we'll have one M02, for example. Oh, no, it starts with the other one. M20, right? So this is something that we have for, okay, so what we have to do for this? We basically, I believe I've done this, but let's just, oh my God, it does not allow me, super. Okay, I mean, you know, how stupid is this? Yeah, but it is behind my bar here. I cannot move it.
Grab the window from the left, probably?
No, the thing that I can do is doing this. No, not even this works. Okay, it doesn't matter. We just don't move it. Just don't touch it. Yeah. So the thing. Say we have this guy. So we want to split this. We have this and we have this, right? We have these two. So Mathematica does not allow me to use the E because it has a different meaning. It's the exponent, right? So let's try to solve this E. I mean, this is how it's usually done. No, this is the wrong bracket. It's the wrong bracket again. So what we are looking for, M20 and M02, right? And you can do this by hand, but that's okay. So this is what you get, and let's just say this. Oh, by the way, when I do it like this, okay, let's you see the trick. Hopefully, it doesn't like it, yeah, but whatever. So the good thing is if I say C form of this, not C from, C form. So we just, I can be lazy and just copy it, right? So, and this was hopefully, wait, now we have to be very sure, I have to check something. Yes. Okay, so yeah. For one thing is we have to call this E again, yeah? And now obviously the difference in the other direction is just that I don't even, I mean, you can look at it, but the difference between the two is that the one has a plus here and the other one has a minus here, right? So I'm not doing this again. So I just put minus here. And it should be 02, the name of the variable. And it should be 02. Okay, so these are these guys, and the epsilon. I think for the epsilon, I don't really need, I just put this here to the other side. Yeah? Okay, let's take this down. So I'll take this here and then I just have to change the sign, and then I'm done with this. Plus 3 times, wait, I have to divide by 3. I have to divide the entire thing by 3, obviously. So, because this was multiplied by 3, so 3. Okay, so then I'm done with this transformation, yeah? Okay, not so difficult. Okay, now the more difficult part is to do the back transformation to the populations. I'm wondering whether I'm going to use, wait, what is this actually? They're all wrong. Okay, so here I have something. I have prepared, so last time we had, okay, so this was the Mathematica file that we prepared last time, where we had this moment thing and we had f in terms of moments. Yeah? So which means we are just using this thing here. Yeah? And for this, to simplify it for me, because they are now called moment 1, 2, and I have to rewrite them. I have here a small, I have this small function here written, and I have these things saved in FFS, and now I can just choose these guys. Yeah, like, okay, what do we want to start with? Let's say we'll usually start with 0, 0, 0. So we'll apply this function, yeah, and this will generate us this here already in C form. Yeah? So this is just our transformation. And now we'll plug these things, we'll plug this thing here. So where we previously had our collision, yeah, we just do the transformation. No, this. So we still use the push scheme here, and we do the transformation. So back transform plus push. Plus push. Okay, so now we back transformed 0, 0. Now we have minus 1, 0. Yeah, minus 1. So minus 1, 0, minus 1, 0. Zuck. So it's complaining here, but I don't care. Minus 1, 0. We plug this here. So it appears to be right? So then there is plus 1, 0. Where am I? So plus 1, 0 gives us this guy. The next is 0 minus 1. 0 minus 1. Zuck. Is this guy. Then comes 0 plus 1. Please look that I'm not making any mistakes, yeah? Because this is difficult to repair later. This is difficult to see. Yeah. Zuck. So now comes MM, minus, minus. minus 1, minus 1. Minus 1, minus 1. So there's just these. Minus 1, minus 1. Now comes plus 1, plus 1. Plus 1, plus 1. So, tick is this here. Okay, maybe I could have done it more efficiently by plus, minus, plus, minus. Plus, minus is this. Plus, minus is this, check. And the last one is minus, plus. Minus, plus. So, of course, as an exercise, you should always do this by hand, but we'll try to get everybody to the Christmas markets today, right? So, in time. Okay. I mean, we can do a little bit of a plausibility check that there must be 2 times minus. Okay, that's. Okay, could be true, right? So then save, we've done this, the collision. We are done with the collision. Actually, we should be done now. The only thing that we have to do now is to put this to our interface, to our Python bindings interface as run MRT. Why didn't I copy this? I'm so stupid. Okay, let's. Okay, let's just copy this and run MRT, and here again run MRT. And now we have to save and pray that we did it correct and that it actually compiles. It never runs the first time. Waiting. Okay, so I did not figure out what these warnings are. Oh, surprise, surprise. Okay, now you remember, okay, I have to restart this. So this was our Python file from last time. I saved it into LBM demo again. And I already played around with this thing here. I already had this, okay, what on earth is this? Okay, let's just remind us. What stupid values did I do here now? LBM demo. Okay, this was the situation that we had. Crit size, velocity, relaxation rate. Restart and run with BGK. So okay, let's remind us this is what happened. Okay, so this is the solution here with BGK. So first test before we do anything fancy is to see whether we had something, whether this is somehow correctly implemented. And in order to see this, what is this? So we write MRT. Now here we get in addition, some nonsense here, the other relaxation rates, for which we now use the same relaxation rate, then it should do the same thing as BGK, right? So this is a test that we should do. It was 9.5, and 9.5. Okay, let's run everything again. Okay, so it looks pretty similar. You get a little bit of this fuzzy thing here. Let's see whether whether we can actually do better, as we said, by putting these things here to 1. Okay? So let's run everything again. Okay? So actually, if you remember that there was some fuzziness here, so this fuzziness appears to be disappeared. Yeah? Okay, looks better. So what did we actually want to do? We wanted to increase this thing here. Let's say to 1.95. So first of all, let's try out what happens with BGK. So run. Boom. Okay? Very convincing. So let's do it with MRT. So obviously this has a much higher Reynolds number, yeah? And it's much more turbulent, what we observe here. I don't know whether it remains stable, but it remains stable for longer. Okay, and now we can play around with these guys here. So for example, what happens if I put for the omega p 1.5? So crashes immediately. We remembered that there was this strange coupling between this omega p and the one for the first order moment. Let's see whether this is already too high. Let's put here 1 point. I mean, we thought they need to be the same in order to be decoupled. Let's just do this, okay? Restart all. You see, it was not that the omega was too high. Yeah? If I set both of them to the same value, it still works. Okay?
But just one question. But I want to see, we have 3 omegas.
Yes.
This function, which one is the omega for all of them? It's the first one?
The omega for all of one is we set this in the constructor. So we have only omega p. So this is omega p, this is omega 3, and this is omega 4. This is the one for epsilon. Okay, now we are not done for today. I have another suggestion, okay? Since we saw them, there is this coupling, somehow we can do something again. And for this, I take the entire thing again. And generate, so copy this and paste it again. So, and here we do it again with just not orthogonal. Yeah? So the one moment that gives us a hard time is this guy. Okay? Forget it. So, instead of this guy, we are just interested in M22, yeah? M22. So, same relaxation. Now we have to plug the equilibrium for M22. The equilibrium for M22 is this one. Am I right with the brackets? Yes. Okay, so, and from here I have to subtract M22. Okay? So, now we're just using countable moments, no orthogonalization, right? And then we don't need to do this. The only thing that we still have to do is to amend this by our new function. So, which we call non-also. Non-also. Okay? Save. Compile. Waiting for the strange warnings. I'm just wondering did it stop running? Yeah, it stopped it running. Okay. LBM demo. So, okay. Let's remind us what we have been doing here. We have to restart to load it again because we changed it, right? So now let us remind when this here is 0, it crashed immediately, yeah? Because these guys are somehow coupled. Why is it not stopping when I press interrupts? You know, we always, okay. So let's, instead of this, use non-also, okay? You know, live action, yeah? What will happen? You see, this orthogonalization couples these moments so that we have to put the same value in this. If we don't, yeah, I mean, maybe it does not work now. I don't know. Let's see when we put them both the same. Should it still works? Yeah. See if, I don't know. Let's do this thing. Run. Okay, I mean, it may become unstable later, yeah? So I don't know whether we check this with the other guy. So we can take this away again. So this one and this 1.5. Okay, run. Yeah? This 1.2, this 1.5, this 1.1. I don't know. I haven't tried this. Oh, this works. See, there are values that work. Okay? So, Li Shi will always tell you, Li Shi Lu. So, if it doesn't work for you, then you didn't try hard enough. Yeah? But you see, if we make this very different, let's say, put this 8. Run again, crash. Use non-also. Run. No problem. Yeah? So actually this orthogonalization, and remember, the funny thing is with this model, there is only this one moment that is not automatic, where it actually matters, where orthogonality actually matters. And making this orthogonal makes it so much worse. Yeah? And in 3 dimensions, there are many of these moments that are not orthogonal, and there it makes it so much worse. Yeah? And you have to be very, very careful in setting these rates that it will not crash. So nowadays you read papers where they have in the title non-orthogonal MRT, where they explicitly say, my MRT is not orthogonal. Yeah? Yeah? Because orthogonality, this type of orthogonality is a problem. However, you still have to come to the next lectures, because the thing is, orthogonality matters, makes a difference, and can lead to better stability if you do it right. The problem is not that, orthogonality in itself is is the wrong way of thinking. It is this kind of unweighted orthogonality is messed up. Yeah? We already talked about weighted orthogonality, and this is a very big difference between weighted orthogonality and unweighted orthogonality. Actually, unweighted orthogonality, it's better you use no orthogonality at all. Yeah? But weighted orthogonality, as we will see, is much better than both of them. Okay, so I guess then I've run enough over time. Yeah, thank you for still, one of you is still here. Yeah.
Do you have maybe time for a few questions?
Yeah, should I stop the recording in between?
Yeah, I mean, doesn't
Yes,
matter.
I stop the recording.